Greetings everyone. I am pleased to present to you our poster presentation entitled Effect of xanthan gum and basalt fiber content on the mechanical behavior of Chlef natural sand. The addition of xanthan gum greatly improves the maximum shear strength, cohesion intercept, and internal friction angle. However, biocemented sand samples have shown an increasing brittleness index with an increase of xanthan gum content. In order to parry this aspect, fiber inclusions were added to the composite. The inclusion of fiber into sand posed great potential to reduce the brittleness of soils and improve its ductility in order to limit loss of post-peak strength. Fiber-reinforced specimens are able to maintain the shear stress with continuing deformation even at large strains, suggesting that these materials are very ductile. The experimental program are laboratory tests performed using the direct shear box on specimens of untreated and treated natural sand with different xanthan gum contents at a medium relative density and different fiber contents under three different normal stresses. The materials used were Chlef natural sand, xanthan gum biopolymer, and basalt mineral fibers. The following figure presents laboratory results of direct shear test on biopolymer treated sand prepared at medium relative density and at normal stress of 100 kPa. From the figure, it is noted that biocemented sand samples show brittle behavior with an apparent peak in the stress-strain curve. A considerable increase of maximum shear strength is observed with an increase in xanthan gum content. Cheng et al. On 2019 attribute the strengthening effect to a condensation and aggregation effect of high tensile xanthan gum gels between sand particles. The maximum shear strength increased proportionally with the increase of gum content. In addition, the residual shear strength of Chlef sand increased when biopolymer treatment was applied. The residual shear strength of biocemented sands at 0.5% was almost 2 times that of natural sand. This increase in resistance is due to an increase in soil rigidity. However, xanthan gum treated specimens have shown a decrease in residual strength after the peak shear strength due to the stiffening of biocemented samples. Figure C presents the influence of xanthan gum content on the brittleness index of Chlef sand. It is noted that Chlef sand brittleness index increased with an increase of xanthan gum content. As previously stated, biopolymer treatment increases Chlef natural sand rigidity, which in turn increases the soil brittleness. This brittle behavior is accentuated at higher xanthan gum contents. The following figure presents the results of direct shear tests on fiber-reinforced biocemented Chlef sand at a gum content of 0.5% and different fiber contents. Laboratory results indicate that a slight increase of maximum shear strength of biocemented samples at fiber content of 0.3% followed by an important decrease at fiber content of 0.8%. However, all fiber reinforced biocemented sand specimens exhibited more strength than natural sand samples. The maximum shear strength values recorded at content of 0, 0.5 and 0.8 were 298, 293 and 213 kPa respectively. Inversely, the inclusion of basalt fiber to a biocemented sand samples increased the residual shear stress. The residual shear stress values recorded were 130, 163 and 194 kPa at fiber contents of 0, 0.5 and 0.8% respectively. From test results, it appears that the residual shear strengths of test specimens to increase with an increase of basalt fiber content. In addition, it is observed from figure C that fiber inclusion seems to have reduced the brittle behavior of biocemented sand specimens. The reduction of brittleness is more important at higher fiber contents. As a conclusion, taking into account the results obtained in the study, the following conclusion can be cited. There is a significant improvement in the maximum and residual shear strength of Chlef sands treated with xanthan gum. All treated samples have shown higher strength than untreated samples. Xanthan gum content greatly influences the strength of biocemented specimens, where it was found that increasing xanthan gum content increased the maximum shear strength of sand. However, the residual shear strength decreased. Biopolymer considerably influenced the stiffness of treated samples and further increased the biocemented sand brittleness with an increase of xanthan gum content. Basalt fiber inclusion significantly affected the maximum and residual shear strength of samples. In addition, fiber inclusion changed the biocemented sand brittle behavior into more ductile one. The influence of fiber reinforcement is mainly dependent on fiber content. Thank you for your attention.